Yeah, we've, the past few tests, I'm thinking integral test and what we talked about last time, comparison, limit comparison. There's some tests that you're dealing, integral test, comparison, limit comparison, you're only dealing in positive terms. Only this, the series only has positive terms. So, that leaves out quite a few things because, yeah, we've got series that alternate term by term, positive, negative, negative. We do have, the geometric series can be both positive and negative terms, right? If the ratio is negative, your terms alternate. So, in a sense, we've got an alternating series test. It's a geometric series, but there's a little more. We can get a few more alternating series in with this this alternating series test. So that's our next one. So here it is. If the series negative, and this will be sort of a generic looking alternating series. You got -1 to the n times this b sub n. So yeah, you kind of break out the alternating signs part with this, and it doesn't have to be -1 to the n. It could be -1 to the n plus 1. So this is just kind of generic form. There can be slight variations, but anyway, if you've got this alternating series, that -1 to the n part, of course, makes it alternating. Where your b sub n is greater than 0. So if that satisfies two things, part 1, b sub n plus 1 is greater than or equal to b sub n for all n. And 2, the limit of the b sub n's as n goes to infinity is 0. So you got two parts on it. That's kind of like the comparison test, isn't it? Where comparison test you had two parts to it. Well, that had to be satisfied. Same thing here. So if that series satisfies that and that, then your series converges. Now, important note number 1 on this is that this test only provides information convergent. It does not, you cannot use this test to show a series divergence. So what that means is if part 1 or 2 is not true, is not satisfied, then the test is inconclusive, okay? If part 1 and or part 2 is not satisfied, or not true, the test is inconclusive. And so, there's variations on these, the comparison test, limit comparison test. Those both can show convergence or divergence. This one only shows convergence. So these two satisfy, it converges. If either one of these doesn't work, you have to say it's inconclusive. Try something else, okay? All right, but that's it. So let's just work through a couple of these and see what happens. All right, so the first one. Is this one. So is that one convergent? Well, I mean, obvious when we use the alternating series test, or when we should try the alternating series test. It's one of the ones that's obvious for the most part. It's when you have an alternating series, which, you know, that -1 to the n, or in this case, -1 to the n minus 1, that gives it away. Okay, so that's a pretty big hint. Yeah, this is going to be alternating series test because, like I said, a lot of those tests depend on positive terms only. And you got alternating signs, that's not going to be good for those tests. And it's obviously not a geometric, right? Geometric is what makes it geometric? It's an exponential function, right? N is in the power. Here you've got n just in the denominator. It's not the power of the number. So anyway, all this points to, yeah, this is alternating series test. So we're going to look at these two things. Now, first of all, both part 1 and part 2, they depend on B sub n. So we need to establish what B sub n here, and sometimes it's more obvious than others. What is my B sub n here?
1 over n. 1 over n.
B sub n is 1 over n, isn't it? I mean, it's not quite in this format because you've got the divide by n there, but yeah, just a slight little adjustment there. Just break that 1 over n out, right? Yeah, so B sub n here is 1 over n. And so we'll start with part 1, B sub n plus 1. Is that,
So won't that fail?
I wrote the test wrong.
Okay.
It's this.
Oh, that's great.
It's less than or equal. Yeah, change. Be sure to change that. That's very important, yeah. B sub n plus 1 is less than or equal to B sub n. Less than or equal to, yeah. What this basically means is it's a decreasing function. If you look at it as a function, is what this means. The B sub n plus 1 term is less than the B sub n. It's a decreasing, it's on the downhill slant there. That's what, yeah, so obviously it should be less there. The n plus 1 term is less than the n term after. Now again, we can use, you know, the same logic that we've used before. B sub n plus 1 would be 1 over n plus 1, less than or equal to 1 over n. Sometimes just looking at it from that perspective gets it. And we'll look at another one where we might have to rely on other things to show this, but that is true, isn't it? Again, denominator's bigger here, so 1 divided by bigger denominator is less than its counterpart over there, right? Okay. Larger denominator. That's true. So yeah, just again, test purposes, tell me something like that to show, tell me that you're not just looking at it. Yeah, that's true. But some reason, you got a larger denominator here, so it's less on the left there. Okay. All right, so that's part 1. Part 2 is label these. Part 2 then, the limit of n goes to infinity of the B sub n's is the limit as n goes to infinity, 1 over n. And again, some of these are easier than others. Yes, that is true. N goes to infinity, so we've got 1 over infinity. That is 0, isn't it? 1 divided by a larger and larger number is 0. So check. Well, if those both check out, then the conclusion is our series does converge. So this series converges, and this is by the alternating series test. AST. Usually it's somewhere on your problem. If it doesn't state which test you use, be sure you know which test you are using. Okay. Any questions on that? Now, here's an interesting side note to that. Do you notice what series that is? Related to, might say? Okay, so that series converges. And that, I don't know why he's in. I mean, it could just be in, but I guess I just wanted to show you a variation. But that is very much related to this, isn't it? The only difference is I've got alternating signs. That is, call it the alternating harmonic series. I don't think they actually call it that, but this one diverges, doesn't it? It's harmonic series. This one converges. So that's just kind of interesting to know. If you just add up, this is what? 1 over 1, 1/2, 1/3, 1/4. You can't do that infinitely. That diverges. You can't add those together. However, if I go, let's see, this one would start positive, so it'd be 1 over 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 plus 1/2. That actually has a value. That converges. So it's kind of just an interesting note there. If you just add them all the positive terms like that, you can't do it. But if you alternate them signs-wise, you can. But anyway, not to blow your mind or anything there, but just gets you thinking. Okay. All right, so here's another. Series is -1 to the n times 3 to the n over 4n minus 1. Is that conversion? Well, like I said, a lot of times these are, they kind of lend themselves to thinking about certain things, but in this particular case, it does alternate. You've got the alternating -1 to the n expression, so it does alternate. So it might be, we're thinking, alternating series test. However, look at this. Let's skip to part 2. Let's say we go through part 1, blah, blah, blah. Part 2 of the alternating series test is where we kind of run into a roadblock. Part 2 of the alternating series test says look at the limit as n goes to infinity to b sub n. Well, hopefully, obviously, the b sub n here is what? 3n over 4n minus 1. And so if we do our limit there, we divide, one way is divide top and bottom by n. You get limit as n goes to infinity of 3 over 4 minus 1 over n, which is top's 3, bottom's 4, minus 0, 3/4. Is that a problem in the alternating series test? Yes, that's not 0. So alternating series test is no good. Now that, though, is kind of a clue as to what to use. Can you think of anything now that we could use instead of the alternating series test? We haven't talked about it in a while, I guess, but remember the old test for divergence? If the limit as n goes to infinity of the a sub n does not equal 0, then the series of the a sub n diverges. Are we gonna have something like that here? Now, we are going back to the a sub n, so let's, that's b sub n. The whole thing combined, that's a sub n. So I'm going back to the whole thing now. So I'm including, for a sub n, I would include the negative 1 to the n. You see what I'm saying? So let's look at that limit. So that would be the limit as n goes to infinity. Negative 1 to the n times 3n over 4n minus 1. Well, same old. I'd still, even though I'm adding the negative 1 to the n, I would still do my divide by n, or I still could do that. Divide by n, top and bottom. I don't do anything with that. Just divide that by n, be 3. 4 minus 1 over n. Okay, well, here's something. We haven't done one quite the same as this before. Because, do you see what's going to happen here? Since it's alternating signs, part of it's going to go to a positive number, right? And the other part's going to go to a negative number. Because those things are going to diverge off two separate ways. You see that if I go with positive n's, it's 3/4, positive 3/4. If n, not positive, if n is even. The even ones will give me positive numbers, right? Positive n's. Because you'll square, fourth, those are going to be positive ones. If I go with odd n's, then it's going to go to negative 3/4. Well, either one of those tells me I'm not going to have a sub n equals 0, right? Either one of those is 0. So this test for divergence works here. If this limit is not 0, the series diverges. And that's clearly what we've got here, right? So this series, negative 1 to the n times 3n over 4n minus 1 diverges, and it's by the test for divergence. TFD. Okay? So not all alternating series. We'll use the alternating series test. Sometimes you can't use it. Question? Is that all right? Okay, here's another one. So this series is negative 1 to the n plus 1 times n squared over n cubed plus 1. Is that converted? Well, again, obvious choice here is start the alternating series test. Doesn't always work out, but usually does. Okay, so again, understand b sub n is the part without the alternating sign part. So it's n squared. It's pretty well blocked out on this one. Now, so for alternating series test, part 1 and part 2. Part 1 was what? B sub n plus 1 is less than or equal to b sub n. Is that true here? All right, well, yeah, this is why I want to show you this one in particular, because the n plus 1 term would be n plus 1 squared over n plus 1 cubed plus 1. Is that less than or equal to n squared over n cubed plus 1? Well, Is that obvious? That is not obvious if that's true or not. The problem is, I increase the numerator, but I also increase the denominator, but I also increase the, you know what I mean?
Yeah.
I increase the denominator here, but I also increase the numerator. And so I can't really tell what's going on because I increase both of them. So, you know, it's not obvious sometimes that plugging that in plus 1 in. So we can look at other really what this, another way to look at this is, this says right here that means that B sub n decreases. B sub n is decreasing. In other words, if I treated this like a function, f of x equals x squared over x cubed plus 1, that function is decreasing. Okay? So let's think about that. How do I show a function is decreasing? Well, technically, calculus way, I show a function is decreasing by looking at the derivative. The derivative is negative, right? That shows me that a function is decreasing, or the part of it is decreasing anyway. Well, you know, the derivative there, you get that, get the critical values, just to kind of review here a little bit. You get your critical values, then you test here, here, and here in each part, which part is decreasing, which has a negative derivative. But, you know, I can see if I'm even on the right track if I just look at this graph. Okay, so this gives me a way to graph it nicely to see. I think I've already got it. Yeah, I've already got it in here, just playing around with it earlier. Yeah, so if I plug that in and look at the graph, so that means, yeah, I've got f prime is negative. So that, you know, if I wanted to verify it for sure, that's the way I would go. Show that it's negative first derivative. But, am I on the right track? Well, this one's more interesting than maybe you first think, because if you look at the graph here, and of course, we're talking n equals 1 to infinity. So I'm only looking at this part of the graph. So if I zoom in a little bit on that, it's kind of interesting because it, I mean, back here on the negatives, but it kind of does this, but then it comes in. And what do you think? You got decreasing, you think?
Not for all ends.
Not for all. Not for all, yeah, because 1 is actually kind of right in here. 1, 2, 3. At 1, say I go from n equals 0. Let's say I go from 0. I could do 0. 0 to infinity. 0 to 1, it actually increases there, right? Then it decreases. It decreases somewhere between 1 and, starts decreasing somewhere between 1 and 2. It actually, you can verify it. This f decreases, what was it? If you go with the derivative, you find out it's the cube root of 2 to infinity. Which is about a little bit bigger than 1. That cube root of 2 there. So, like I said, it's a little more interesting than you might think. I mean, a lot of you can see it's obviously decreasing, but this one has that little blip in it. So, now if you go back to the statement, it said for all n. Well, to get by that, one thing we could do is it decreases here, so I could say 2 to infinity, and then it's for all n. Really, a finite number of n's that it doesn't decrease for is okay, but if we started at 2, that would get out of the problem area there anyway, so. Okay? With me there? So, yeah, it's not always a given that this decreases, so sometimes you have to rely on some other things instead of just doing this. You see what I'm saying? Okay. All right, then part 2. Of the alternating series test, what is it? The limit as n goes to infinity of the b sub n. Hopefully that'll be a little easier here. So that's n squared over n cubed plus 1. Yeah, just do that limit. Easy enough to verify that. Divide top and bottom by n cubed. And so that would be the limit. As n goes to infinity, n squared divided by n cubed is 1 over n. N cubed divided by n cubed is 1. 1 divided by n cubed is 1 over n cubed. Well, that goes to 0. 1 plus, that goes to 0. Yeah, you got 0. So check. Check. So this one does converge by the alternating series. Converges. Alternating series. Okay, we good?